So as you can see, today we're going to talk about solving multiple step equations. A big piece of this is going to be using your background knowledge. Lucky for you guys, you had an excellent pre-algebra teacher last year, so you should know the basics behind this, and you really should. It should come right back to you as far as how we go about this. Some quick reminders as far as your background knowledge. You need to ask yourself, what's your goal when solving equations? What do we use when solving equations? And what's that rule that we have to follow when it comes to balancing the scale as I work those equations out? Remember, we're starting with two things that are equivalent. We want to keep them equivalent no matter what we do. There's the key rule of algebra there as far as when we solve equations, thinking balancing that scale. So if, in case you forgot, this is what you're looking for. Our goal is to isolate the variable on one side of the equation. How we're going to do that is we're going to use more than one inverse operation. Because they're multiple step equations, it's going to involve multiple inverse operations. And then the other key would be whatever we do to one side, we must do to the other. All of that is a refresher for you. And hopefully remember the idea of multiple step equations. We use the cover-up method. And this first example is going to go over that again, and then we'll kind of, hopefully we're sparking it in our background knowledge and we'll be good to go. So we'll jump into the examples, keeping those ideas in mind. First example I see is 3x plus 7 equals 19. So we know that 3x plus 7 is the same thing as 19. And as long as we do the same thing to both sides, and as long as we follow the rules of algebra and the rules of arithmetic, we should be fine. The cover-up method, the idea is cover up the term with the variable. And so what I mean by that is I'm literally going to cover up this term that includes the variable. And I'm going to isolate whatever's underneath that box. Whatever's underneath that box, I want to get it by itself. And so to do that, I'm going to use inverse operations. I see that I have plus 7. In order to get rid of plus 7, I'm going to subtract 7. But whatever I do to one side, in order to keep the scale balanced, I got to do that to the other side. So I subtract 7 on the other side. Notice positive 7 minus 7, that cancels out, that goes away. And I'm left with whatever 19 minus 7 is, which is 12. So my box, whatever's underneath that box, equals 12. Well, now I'll uncover that and I'll bring that down. And so now I'll notice that 3x equals 12. Now the goal is to get x by itself. 3 times x, that's multiplication. Use the inverse operation, use division, divide on both sides, and x equals 4. Now remember, we're not going to do it on this video for sake of time, but to check this answer, I can always use substitution back into the original equation and check and see if that works. If you get a true statement, it did work. If you get a false statement, you might want to rework it. Another example, let's say the variable's on the right side of the equation. Doesn't matter. I'm going to cover up the term with the variable. Think that I'm covering up the x divided by 2. I'm covering up x divided by 2, and I'm trying to get that by itself. To get rid of a minus 1, I'm going to add 1 on the right side. If I do that to the right, I must do that to the left. So notice I have a negative 3 plus 1. I know they're battling. The negatives are going to win, and they're going to win by 2. So I have negative 2 equals whatever x divided by 2 is. I'm still following those same rules. Try and isolate the variable. Whatever I do to one side, I must do to the other using inverse operations. X divided by 2 is my problem now. I want to get rid of that divide by 2, so I'm going to multiply by 2. Remember, I want to do that on top, so it actually cancels out. But if I did that on the right, I got to do that to the left. A positive times a negative gives me a negative, and it looks like x equals a negative 4. Stay with me on just a few more examples. This is a little different because there's a couple things happening here. You see there's an operation in the top of my fraction. When I cover this up, then what I really want to think is that I'm going to cover up the top of my fraction. I'm going to cover up with the x plus 3. Get rid of whatever's not the x plus 3. So in this case, x plus 3 divided by 2. I need to get rid of that divide by 2. Just like before, I'm going to multiply by 2 on the top, and I'm going to multiply by 2 on the right side. These 2's cancel out. Now whatever I had covered up comes back down. X plus 3 equals, what's a negative 5 times 2? Well, that's negative 10. Last step to get x by itself, use the inverse operation of addition, which is subtraction. And notice I have a negative 10 and a negative 3. They're coming together, and x equals negative 13. Again, if I wasn't sure, I could substitute all the way back into the original equation. I'd be good to go. Last 2 I would star in my notes. These will be the most helpful for you going forward because they deal with your favorites, fractions and decimals. In this case, I have 2/10 x minus 3 equals 9. I'm trying to solve for x. Biggest tip I probably have for you here is the idea of getting rid of decimals. To get rid of a decimal, I multiply by a power of 10, 10, 100, 1,000, whatever the case may be. Since I have one decimal place here, I just need to multiply by 10. But if I'm going to multiply this term by 10, this first term, remember I have to multiply everything by 10. And so in order to do this, I'm going to use a little bit of distributive property from the other day. I'm going to take 10 times 0.2x plus 10 times a negative 3, which would equal 9 times 10. Everything's getting multiplied by 10. This moves the decimal one place, so I have a 2x. 10 times a negative 3 is negative 30, and 9 times 10 is 90. So I have 2x minus 30 equals 90. Now it's back to that same idea. Cover up the 2x, get rid of the minus 30, and so 2x equals 120. And then I notice that x will actually equal 60. If you don't believe me, plug that back into the original equation with the decimal, and you'll see that that absolutely works. As long as I do it to everything, I can manipulate the equation that way. Similarly, if you see this situation where you have fractions, and I know you guys don't like fractions, To get rid of fractions, we don't want to multiply by powers of 10. That works for decimals. In this case, I want to multiply by the least common denominator of all the fractions. So if I have 1/2 and I have 3/4, I need to think to myself, well, what's the least common denominator? And in this case, the least common denominator between 2 and 4 is the least common multiple between 2 and 4, which is 4. That means I'm taking 1/2 y times 4 plus 3/4 times 4, which equals 5 times 4. Got to do it to everything. Notice half of y times 4. Well, what I want to do here, rearrange this like we worked on the other day, simplifying, put the constants out in front. Half of 4 times y, that's going to be 2y. When I look at this, remember the 4's on top, so those 4's can cancel out, and I'm just left with 3. 2y plus 3 equals 20. 2y plus 3 equals 20. Now I'm trying to get y by itself. I subtract the 3 on both sides. 2y equals 17. Last step, divide both sides by 2. Remember, improper fractions are good fractions. We like them better than mixed numbers. So y equals 17/2, and I'm good to go. That's really the basics of solving multiple step equations. As long as you can remember that your goal is to isolate the variable on one side of the equation, you're going to use more than one inverse operation. Whatever you do to one side, you must do to the other. And then, of course, keep the cover-up method in mind. Hopefully the allergies didn't cause my voice to be too bad, and hopefully we got all that down in our notes for class.